Thank you so much, Professor Archer. It's a pleasure to be here. This is my first visit to Cornell, and it's been a wonderful experience. Well, first visit for a very long time. A lifetime ago, I used to play soccer at UPenn, and so we would come up here and play against Cornell, usually pretty early in the year to make sure that we avoided the weather. So Professor Archer gave me a wonderful introduction. I maybe will want to reiterate maybe one point here. Can folks actually see this? Should I dim the lights? Is it okay? Right.
Let's see here. There.
Oh, yes, wonderful. And so one of the things that we've sort of started to think a little bit about is how do you get beyond saying we need better batteries? I think everybody can agree that we need better batteries, but it's kind of a motherhood and apple pie type statement where everybody can agree on that, but what does a better battery look like? How much better does it need to be? And where should we be spending time and effort? And so much of this talk will focus on trying to understand what is the best way to approach designing a system and how we can go to basically from doing fundamental science to doing target-informed fundamental science based upon our knowledge of what our system design needs would be. And so perhaps I can start with a place where I think everybody might agree. Many of you have seen a graph like this before in some way, shape, or form. It's essentially looking at energy consumption and trying to project out worldwide energy consumption in the immediate future. And what you'll notice is that worldwide, we're expecting energy consumption to continue to increase. I actually think this is a good thing. This is reflective of increases in quality of life around the world, a burgeoning middle class, improvements in life worldwide. The challenge is, of course, what this energy consumption is connected to. And the challenge is that with this increased energy consumption comes carbon emissions, right? And if we're intrinsically coupling energy consumption with carbon emissions, we start to run into problems related to climate change. And so the second graph I'll show you here is some emission scenarios that I pulled from the Global Carbon Project. And this essentially looks at the idea of net CO2 emissions. This is where we are sort of tracking along here, this Keeling type curve, and trying to understand how these changes in net carbon emissions are going to impact either changes in the global temperature or changes in sort of the radiative forcing target, right? So this is the difference between the amount of energy that comes in and the amount of energy that will come out of the global climate, and that's related then to heating. So the more the delta is, the more heating that you have. And what you'll notice here is that sort of the baseline approximation, so sort of if we do a business as usual case, we're moving up, 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 and there's some range in the models right here, but you're around 4 to 5 degrees or greater. And if we actually want to keep it down below 2 degrees Celsius, we actually need to figure out a way not just to stop increasing net emissions, but actually to reverse them and begin to go negative by almost 2080 here, right? So this is a fairly significant challenge that one can imagine. And 2080 is not that long of a time scale in terms of making changes like this. And so we're at a point in time now where if we're going to act, we're going to have to act pretty quickly, and we're going to have to act pretty drastically. So we're already beginning to move forward. And so this is an example I'm showing you of utility scale power purchase agreements for solar, right? This is in the United States, and this is the levelized cost of solar over the lifetime of the installation. And what you're looking at here is a range of contracts, 232, which total to 14.5 gigawatts AC. And what you see here is the size of these bubbles represents the size of the installation, and where it is on the y-axis here represents how expensive it is at the time. And what you'll notice is over the since 2006 or so, we've seen these costs come dramatically down. Each of the colors here represents where the installation is. So you can see, for example, in the Southwest, as you can imagine, this is quite a delightful value proposition. But say up where we are in the Northeast, okay, maybe this is a little bit more expensive due to the solar insolation in the area. But in general, you can see that these costs are coming down dramatically. If you and I were standing here having this discussion 10 years ago, I don't think anyone could have predicted how fast this was coming down. So this is an example of a successful story in terms of technology deployment. And in fact, if you then compare it to levelized cost of stored of electricity, excuse me, for a range of other opportunities going from concentrated solar power, coal with carbon capture, all the way down to wind and natural gas and hydro, solar is already coming out on the bottom in most regions such as the Southwest, but of course in other regions we're going to have to think about how we're coming down. Now, if I take a step further out and say the US is not the only people who need to act here, you can look worldwide that unsubsidized PPAs are even lower. So these are just examples of PPAs in Peru, Mexico, Dubai, and Chile. And you can see, of course, solar power is becoming cheaper and cheaper. So this is a good sign. This means that we can think about decarbonizing electricity generation. But there's a rub here. And the rub is intermittency. And so what I'm showing you here is some data collected by Patrick Brown at the MIT Energy Initiative. This is the hourly variability of wind and solar resource in Texas. So this is now in that southwest or southern region in 2014. And what you're looking at here as you go down, this is January to December. Each of these is about 24-hour period, so you can sort of see the sun going up and the sun going down. That will be in red. In blue is the wind. And the black line that you're sort of tracing along here is the load or the demand. So what you'll notice here is that there are periods of time when we have overproduction. So say we'll take this couple of days here in January. There was a lot of wind, and so there's overproduction here, which would lead to then some curtailment. And so things are good. We can run almost entirely on renewables. But you'll notice almost a week later, you have a period of time where I don't have enough sun and I don't have enough wind. And so for a couple of days, I'm not going to have enough solar or wind for me to be able to support the load in the grid. And you can even begin to look along here, and you can see even down here in December, we've got about a week or so where we're really hurting, right? We don't have enough to give us the power that we need. And you'll also notice another aspect here, which is seasonal. For things like December and January, you can see that there's less solar. And when you look in the middle in the summer, there's lots of sun, right? Makes sense because of the way the days work. We have longer days in the summer and we have more sun, and in the winter you tend to have less. So all of this, what this tells you is that while we need to have daily storage in order to, say, move solar energy from the peak of the day into the evening, you're also going to need to have storage solutions that are going to be multiple day, and even storage solutions that may be seasonal as we get greater and greater penetration of these resources that are intermittent. So there's intermittency off of different time scales. And for this, we're going to need to start thinking about different energy storage technologies. This is one way to go forward, and this will be the way I focus the rest of the talk on today. But what I want to make everybody understand here, hopefully that you take away from this, is while I'm going to talk to you about a way to maybe make renewables or the grid a little bit more efficient by integrating electrochemical energy storage, there are also aspects in research going on here in Cornell focused on batteries that would enable transportation and the decarbonization of transportation. These two are intrinsically linked to one another. If you decarbonize transportation, but you still have to think about where the electrons are coming from, and so we need to decarbonize both of these sectors. And once you enable this, if you have treat electrical energy, there's lots of very interesting things that can be done within industry. You can think about using electrical energy very simply to, say, power boilers to generate steam. But perhaps more interestingly, you can think about what can electrochemistry do in terms of imparting unique reactivities to maybe revolutionize the way we synthesize fuels and chemicals. I would love to talk about these, but as I understand, this class is a little bit less than an hour, and so I'm going to solely focus on the electricity side of things, but hope that people understand that the methods that I'll talk about are portable and can be applied to these other sectors. So far we've talked a little bit about fossil generation and the integration of renewables into fossil generation and the coupling then between this generation and the demand that's coming from industry and coming from residential and society in general. So how do we typically store electricity now if I want to decouple that? And typically we're using pumped hydro. Pumped hydro makes up about 95% of the world's energy storage. And they look something like this. So this is an example, apologies for that, of pumped hydro storage on Lake Michigan. So this is Ludington, Michigan. What you're looking at here is this is the lake right here, and then this is the reservoir for energy storage. This reservoir is at a slightly elevated height, And so what you do is you pump water uphill into that reservoir when you want to store energy. Then when you want to actually harvest the energy, the water will flow down through a turbine station, and you'll use the rotations of those turbines to generate electricity to deliver to the grid. This is a very inexpensive way of storing electricity as long as you have geological architectures on your side. That is to say, I don't necessarily have to pay for the lake. The lake is already there. All I need to do is build a pump station or a turbine station, and I need to dig out a reservoir right here. So you can also imagine that if I wanted to store energy for a long period of time, this actually has very favorable scaling. The size of the reservoir determines how much energy you store. So the larger the reservoir is, the more power I can deliver for a longer period of time. And then the size of the power station determines sort of the rated power that I can deliver, right? So you can imagine for longer duration energy storage, you're going to build a larger and larger reservoir or more reservoirs. You don't necessarily need to build a larger pump station. As a result, the cost of this system begins to asymptotically approach the cost of storing the water in the reservoir, and the pump station becomes a smaller and smaller part of the cost as I go to longer and longer durations. And this is what leads to it being very cost effective for longer duration electricity storage. The trouble, of course, is geological architectures, right? Here, you might be able to maybe do pumped hydro because you have the Finger Lake and you could maybe have a reservoir on top of a hill. For me in downtown Boston, this is an absolute no-go, right? So we got to figure out a way to be able to store electricity without necessarily being limited by my geological formations. And so the way that we start to think about that is to use batteries and to say, well, can I think about using electrochemical energy storage to do something similar to pumped hydro? And I want to mention here that most folks, I think, in this room are very familiar with batteries that look like this. Enclosed, could be a Duracell AA battery, could be a lithium-ion battery, where you have a compact form of energy storage that powers our portable electronics and is actually now emerging in things like automotive applications. However, when I go to the grid, what I'm really concerned about is price and lifetime. My cost optimization is I need it to be as cheap as it possibly can, and it's going to be a big project, so in order for me to recoup my expenses, I need it to live for a very long period of time. Energy density is only an input that serves to enable price and lifetime, right? And as a result, what that means is that I don't necessarily need to have an enclosed battery. I can have batteries that begin to look more like a chemical plant, where now I'm separating a reactor out and I have storage tanks and pumps and heat exchangers and all of that. And they're able to do that because I'm saying that my space constraints are no longer such a big deal. I can maybe get to cheaper systems if I get to these new designs. And that's what I'm going to talk about from here on out. But for those of you who are pretty astute, this looks a little bit like the pumped hydro that I showed you the other time. And I have separate tanks, and I have now, this is my turbine, my electrochemical turbine, so to speak. So how many people here are familiar with redox flow batteries? Maybe show of hands. Okay, a few people. That's okay. There's no quiz. So I'm going to go through some redox flow battery fundamentals, and I think this hopefully will be useful as we go forward to understand some of the points that I'm going to make later about the unique aspects of this architecture. So the redox flow battery consists of two tanks that store energy, that have energy storage or charge storage materials that are pumped through an electrochemical reactor to oxidize and reduce these materials to store and release electricity when we want it. So within the tank, you're going to have three components generally. You're going to have an active species. This active species is what actually will to convert the electrical energy into chemical energy through redox events. And you're going to have the active species dissolved in some supporting salt and solvent. So in this case, I'm showing you a vanadium sulfate, and that's typically dissolved in something like sulfuric acid and water, right? And what these systems will take advantage of is that there are different redox reactions that occur at different free energies. So they're occurring at different potentials. And the cell potential between these two redox reactions now tells me how much energy that I can store in my system, right? And so when I charge and discharge, I'm simply converting from electrical energy to chemical energy, and the cell potential is then related to the Gibbs free energy that I can store. So how much energy I can store in this particular form. And so I can charge and discharge with which to get my energy storage in and out of the battery. I actually do these reactions in an electrochemical cell that looks a lot like a fuel cell to those of you who might be familiar. It's a multi-layer system where I have now these two electrolytes come in, they go through flow fields and electrodes, and they're separated by a thin membrane to keep the streams from mixing. So I'll break this down a little bit more. So an important component here, we'll start off in the middle, is the membrane. Typically in a flow batteries today, we use what's called an ion exchange membrane. It's selective for allowing certain ions to move through while blocking others. What we want is we want our supporting ions, in this case for a vanadium system, protons, to move freely through this membrane to allow us to balance and maintain electroneutrality. So as electrons go across, we're also going to need ions to go across to maintain electroneutrality. But I want to be able to block my active species from crossing over. If my active species cross over and mix, after a short period of time, all my tanks are going to be purple, right? And if my tanks are going to be purple, I'm not going to be able to recover that type of material, okay? So what actually happens is these ion exchange materials are typically perfluorinated type membranes, things similar to something like Nafion from DuPont. Because you're dealing with relatively concentrated solvents or electrolytes outside, things like charge selectivity become a little bit challenging because the concentration of ions outside of the membrane is oftentimes greater than the concentration of ions within the membrane, which means that you sometimes will have things like salt penetration where all the supporting salt will rush into the membrane and it begins to function a little bit more like a porous plug. So separations in flow batteries are usually a combination of charge selectivity and size selectivity as well. And we'll come back to that because it's something that we can use to our advantage. So how do I actually get towards the membrane? I need to introduce my liquid electrolytes from the tanks, and they're introduced through various flow fields. This is an example of an interdigitated flow field. What you can hopefully see here is these are open channels right here where my liquid will flow into my cell, and you can see that they're dead-ended. And what that means is that they need to be able to jump over this black part right here, which is a rib. If I flip this on its side, what you'll see on top of here is a porous electrode. And so what you expect to see is that these materials will jump into the porous electrode and then jump into another channel that's adjacent so they can move out of the cell. So I have forced convection through an open channel and then through porous media. And if I look more closely at my porous media, it looks a little bit like a paper, a carbon paper right here, where I have relatively large pores that enable me to flux through there with relatively low pressure drop. So my electrolyte is moving through here with forced convection, and then there's a diffusive flux to my electrode surface where my electrochemical reaction occurs, and I change my system, and I move back out and move back into my tanks. So hopefully that made a little bit of sense right there. And for those of you who are from an engineering background, what you can probably see here is I mentioned thermodynamics, I mentioned separations, I mentioned transport, and I mentioned kinetics. And you can also think that process design and estimation come into this as well. So this is an engineer's playground, in my opinion. And so why would you be interested in an architecture like this? Well, first of all, you decouple power and energy scaling. The energy is determined by the size or the amount of material in your tanks, and the power is determined by the size of your reactor. And so what you can imagine that is if I need to store more energy, I can just get more tanks or put more material into my tanks. And if I need more power, I can build out another reactor, right? This is different than, say, an enclosed battery where I have to buy everything at once, and so I don't have any benefit of scaling. And in the next slide, I'll show you how that actually plays out. Relatively simple manufacturing as compared to, say, thin film type lithium-ion batteries. High durability and low maintenance. In principle, if you have this recirculating electrolyte, you can take this system offline. You can, say, replace the contents of the tank quite easily. You can refurbish reactors. It's a lot easier to take this apart than it would be, say, for a system that's enclosed together. And finally, location independence, and this is, of course, a shout out to pumped hydro. I can put this in downtown Boston should I wish. But there's no free lunch. And the challenge here is that redox flow batteries are significantly less energy dense than enclosed batteries. So a lithium-ion battery is going to be much more energy dense. That should make sense to everybody because what I'm telling you is I'm taking an active material and dissolving it in an electrolyte versus in a lithium-ion battery, the active material is actually solid state, right? So necessarily it must be more energy dense. And so the rub here is that I'm using redox flow batteries for grid storage applications where I told you energy density isn't my main design factor, it's cost and lifetime. So this is just an example of a vanadium redox flow battery. This is present state of the art. So for example, if Cornell wanted to buy a redox flow battery or anybody wanted to buy a redox flow battery, you'd probably be looking at vanadium redox flow battery vendors. The way this system works is that you take advantage of the fact that vanadium has 4 stable redox states within the water window. And so you're able to charge vanadium 4,5 and reduce vanadium 3,2 to charge the battery. And then to discharge the battery, you take vanadium 2, oxidize it to vanadium 3, and reduce vanadium 5 to vanadium 4, right? The nice thing about this particular system is that if I don't have a perfectly perm-selective membrane in the middle right here and my ions mix, it's all the same parent compound. And so periodically you can rebalance the tanks to get your system to operate for longer. So it's quite robust in that fashion. And because it's an aqueous electrolyte, there are a few less challenges in operating as compared to operating with a non-aqueous type system. The disadvantage is that vanadium is quite expensive. So vanadium right now actually has gone through a spike. Recently, the Chinese steel industry increased the quality of steel, which means they need to put more vanadium into steel. Steel is the main use of vanadium right now. Vanadium redox flow batteries, therefore, are price takers. They tell us how much it is, and we buy it at how much they say it is. And so, of course, if the price of vanadium goes up, the cost effectiveness of this battery is hurt dramatically, right? I think the cost will come down. They are coming back down, but this is a tough business to be in, at least in the near term. The second is, of course, the limited energy density. At some point in time, you have to figure out what are my installation costs going to be. Those will eventually play a role. So the value proposition of flow batteries is long duration. And I want to remind you of the graph that I showed you from Texas a few minutes ago, where I mentioned that we have to think about energy storage on multiple time scales, right? I said we have to think about it intraday, intra-week, intra-month, and maybe intra-year or seasonal. And what you can see is that as renewables penetration becomes greater and greater, we're going to become increasingly concerned about these fluctuations. And so we're going to need to think about what kind of energy storage devices are going to allow us to live in such an environment. And what I'm showing you here is the scaling in terms of a battery capital cost as a function of discharge duration. And what you can see for flow batteries, for example, all the flow batteries are the curves right here, starting off with vanadium, and this is an example of a vanadium vendor right now from Massachusetts. I'm being a little bit of a homer right now. But what you can sort of see is that the vanadium cost kind of goes through a knee, and it's the case for all of the different flow batteries that I see. We always will go through a knee. And what you're looking at here is the transition between the cost where power is going to be quite important to a cost where energy is going to be important, where you're asymptotically approaching the cost of the materials that are in the tank. I mentioned to you that vanadium is expensive. So this is the rub right here. If vanadium is expensive, even if we make a system that is entirely based on vanadium and the cost of the reactor is almost negligible, the cost of vanadium may price us out of a particular market, right? We can imagine that in the future we're going to be able to get economies of scale, we're going to be able to build better reactors, and so we can imagine the cost of the reactor coming down that might push this curve a little bit to shorter time scales. But fundamentally, if we don't think vanadium is going to get cheap enough, at some point in time, even though we have scaling advantages versus lithium ion, we're not going to be able to play in the space, right? Now, what would be interesting is, can you begin to identify also new redox materials that are dramatically cheaper than vanadium or have some benefits that might allow you to get to now these lower costs out here, that now will allow me to get to systems that are transformatively cheaper than where we think lithium ion can go, and maybe that gives us enough of a leg up. And so that's sort of where we're thinking about. And so, of course, there are two things to consider as we move forward. The first is that flow batteries are a nascent technology. Remember I showed you from 2006 the cost of solar has been cratering, right? That also seems to align now in an opposite correlation with the amount of activity in vanadium or redox flow batteries in general increasing, as all of a sudden we become increasingly interested in the fact that we're going to need grid-scale energy storage. I want to draw your attention, though, to the magnitude of this scale. This is an imperfect metric. Of course, I'm basically looking at vanadium flow batteries and doing a Web of Science type analysis. But if I did a similar type analysis for lithium-ion batteries or a similar type analysis for fuel cells, I'm maybe 1 to 2 orders of magnitude off. That is to say, there's way more activity in those areas right now, and that activity has been sustained. As a result, we're still quite early days. The second is that if you go back to the previous slide that I showed you and I put the Vionics flow battery chemistry on there, in 2014, these costs are on the order of about $500 per kilowatt hour, and the DOE would like us to get to about $150 per kilowatt hour. So we're about threefold off at this point in time. So there's a need for innovation. There's a need to kind of close the gap here. And so what I see here is opportunities for transformational technology advancement through either the development of new redox chemistries or the advancement of reactor designs. I'm not alone in this space. There are many different people who are quite interested in these types of technologies, and there are a range of pathways going forward. So if you went and looked up new research in vanadium redox flow batteries, you'll see that there's a tremendous effort to get away from things like vanadium to look at, say, organic or polymeric type active species. The reason you like organics or polymerics is that in terms of organics, that gives you some design flexibility in terms of controlling different aspects of your redox molecule. In the terms of polymerics, you can then think about going from an ion exchange material to a size selective material that looks a little bit more like a filter. And that way, if your polymerics are large enough, they're not going to go through that membrane. And these tend to be significantly cheaper than the ion exchange membrane. So going entirely to size selectivity. As we start to look at these new materials, we want to also expand our design space. So we want to get away from aqueous acidic, where a lot of these types of organic materials aren't necessarily happy all the time. So can we think about going to neutral pH? Can we think about going to non-aqueous that might allow us to get to higher cell voltages? And this is an area of particular interest for me. And then also, can we think about cell design? And so rather than taking cell designs that are borrowed from fuel cells, because those are our more advanced cousins, how do we think about then going to systems that are specifically designed for redox flow batteries, where we have a deeper understanding of the transport and the kinetic rates that go on in those systems, and then how one would design a battery around that? So there's work going on in all of these areas. And one of the things we started to think about was, what does success look like? So if we're all working hard in all of these different areas, how do we know that we're getting anywhere, right? So we could spend a lot of time designing new organic materials, but our limitations may turn into what kind of solvents we can use, what kind of membranes we can use. And so how do we think about the system as a whole and try to identify what favorable combinations of each of these areas would lead me to the lowest cost battery, rather than focusing solely on each one of these individually and trying to optimize them, or maximize them rather. And so this brings me to my academic grandfather, George Whitesides. And one of the things that George Whitesides pointed out in this rather long quote, you can focus a little bit on the stuff in the red, is the use of models. That is to say, models are going to play a very important role in terms of us understanding more complex classes of related systems, and to help us focus on particular tractable research ideas. Remember, I started this talk saying we need to go beyond better batteries. Better batteries is something that we all agree upon, but it's not a tractable research direction. Like, what would you do, right? And we try to think about ways that we can use models to represent and help us to understand what is needed on a basic science side. I want us to think about models very generally, though. So typically when you think about models, everybody might have their own idea. It could be a DFT model. It could be techno-economics. It could be, some sort of mathematical description. But models are very general and should be viewed in the broadest sense. So it could be very well a techno-economic analysis, which is what I'll talk about almost immediately after this. But I'm also going to give you examples of models where we can think about different reactor designs that can teach us something about transport or kinetics in the systems that we're interested in, or thinking about model redox couples that we can use with which to probe different performance aspects. So models should be thought of very generally rather than saying, oh, it's just on a computer or something like that. And so I'll start off with techno-economic modeling. And the reason that we started to look at techno-economic modeling is we thought it was a useful way for us to begin to assess a design space. We said we have a certain desired system costs set by the DOE or set by any other set of metrics, and we have a certain performance that we'd like to hit in order to get into that space. Now, traditionally, when you think about techno-economic modeling, you think about taking a new material. It could have a different property, a different cost, or a different performance. You plug it into an existent system, and you see, did my performance improvement offset any change in cost, right? And therefore, am I going forward or am I going backwards? That works really well in existing systems, but if you're talking about conceptual systems, it's very hard to design in that fashion. And so what we thought of is maybe we can solve this problem in the inverse. So if I have an idea of what my system cost needs to be, and if I have an idea of what my performance needs to be, can I solve this problem to get a solution space where I can identify the combinations of materials, properties, cost parameters, and component performances that would allow me to get to some solution over here that would be viable? And so what we're thinking about is connecting materials properties to system targets. And this could take the form of understanding critical sets of interdependent materials properties that allow us to understand how we can design in this space, how design decisions on the material scale will impact other aspects of the system. For example, if I wanted to use a polymer, I can use a polymer in a flow battery that will allow me to get to a cheaper separator, but pumping a polymer is no joke. So have I actually gone forward, right? And then what technical roadblocks might be obscured on the component level where I'm looking at one component and I'm missing, something bigger in the system. And so that was the goal of this techno-economic analysis. And so our approach has been to consider best case scenarios. So when we look at techno-economics models, we consider a future state where we have economies of scale, high volume production in a competitive market. This is an imperfect analogy, but you consider this to be the thermodynamic limit of cost, right? So if everything breaks in your favor, this is how long you think the cost can go. And if you can't hit your target when you get to that limit, you're probably never going to get there. But if you hit it, you have some senses this might be a good pathway to go down. Because we're dealing with new systems, we use hybrid bottom-up and top-down approaches where we borrow from systems that we think are quite similar, but sometimes we need to build from the ground up. And then also, I'm an academic, but this is a very difficult thing to do alone as an academic. One very simple thing is I don't know how much things cost. I know how much I buy them at Sigma, but I don't think that's the real cost of materials. And so having industrial partners and folks at the National Lab really help you to understand what is the true cost or what are things that really keep them up at night that allows us to get to a stronger model. And so what I'm going to show you on the proceeding slides will be a model that focuses on hitting a target that was set for us by J. Caesar. So this was the organization that I'm a part of. And what we're looking for here is to try to understand for 5 hours of energy storage, how do I get a $100 per kilowatt hour battery, excluding the inverter and installation, that will operate for 7,000 cycles or 20-year life. If you run the numbers on this, this is about a cycle a day, so we're only looking at intraday type cycling. And what I'm going to do is simply try to figure out what the price of the battery is by adding up the area, the materials, the overhead, and the system. And what I'm going to do is I'm going to assume an inverter cost of about $20 per kilowatt hour. That aligns with the sunshot goals for DOE. And I'm going to assume an installation cost about $30 per kilowatt hour. If you add those together, that takes me up to $150 per kilowatt hour. And so I come in right around where the DOE wants me to be. So being a chemical engineer, the first thing I learned is I need to draw a control volume. And so if I draw a control volume around my flow battery, I basically want to say everything within this box has to hit $100 per kilowatt hour. So this is my price divided by my energy storage. And I'm going to have to pay for a reactor. And I'll need the cost of the reactor needs to go in there. The cost of the electrolyte, the salt, solvent, and active species, the tanks that you actually need. Balance of plant, which is tanks, pumps, pipes, heat exchangers, the whole kit and caboodle, which is all the other stuff that you need for the battery to work but doesn't actually store energy. And then if I want it to be a price, I need additions to cost. So this is depreciation, labor, overhead, and a profit margin, which is what makes it a price. And I'm going to consider here the present and future state battery costs with no installation, as I talked about earlier, and no inverter. And so if I break down now the cost of the reactor a little bit more, the cost of the reactor is directly proportional to the cost of the materials that will go into the reactor. That should make sense. If I put more expensive materials in there, that's going to affect the cost. And the resistance of the reactor is going to be directly proportional to the cost. So the higher resistance that I have, the bigger the reactor I'm going to need in order for me to meet my power target without losing efficiency, right? So if I have a lower resistance reactor, it can be smaller. And it's going to be inversely proportional to the square of potential. What this tells you is that potential is a huge factor in terms of how, and potential here is my cell voltage. So the higher cell voltage that I have, my reactor is going to become increasingly cheaper. So this is a really big knob for us to begin to play with. I mentioned to you cost earlier, and I said I don't really know how much things cost. I know how much I pay sigma for them. The cost here is a difficult thing to figure out. But we're fortunate in terms of flow battery reactors look a whole lot like fuel cells, and so I'm able to take advantage of what the DOE has done in terms of PEM fuel cells and saying I'm going to be able to take these numbers and figure out where they're going to go in the future. So this is a benefit of having a more advanced cousin. Then I want to think about my electrolyte cost contributions. And so my electrolyte cost contributions can be normalized by my discharge energy. So this is how much electrolyte I need for a 5-hour discharge. And it's going to be made up of my active materials. I need both a positive and a negative active material. It's going to be made up of my salt. So this is a supporting salt that's required for my system to operate. And it's going to be made up of a solvent, right? So what is everything dissolved into? If I take, for example, say, an aqueous battery, say we'll take vanadium, for example, the cost of sulfuric acid and water is significantly lower than the cost of vanadium. So these terms you can imagine are going to be minor contributions, and your major cost contribution is going to be the active material vanadium, which is what's driving us towards getting to inexpensive materials such as something like an anthraquinone, which I'll come back to, which may allow us to get to significantly lower costs. The other way we can get there is we can go non-aqueous, and non-aqueous would allow us to get to this higher cell voltage right here, but the penalty is, so if I think non-aqueous, think about a lithium-ion battery versus say a Duracell battery, where the Duracell battery is about 1.5 volts and the lithium-ion battery is about 4 volts or so that you're operating with. So that's a pretty big jump. The rub for that is that while my active materials might be cheaper, I could maybe still use some organics. I have to pay for the lithium-ion salt, which is quite expensive. It's typically fluorinated. And I'm going to actually have to pay an appreciable amount for my solvent. It could be something like propylene carbonate or acetonitrile, which are used on the large scale industrially now, and so they might not be that expensive, but it's not as cheap as water. So I need to make sure that I offset these additional costs that come in with the fact that I'm going to higher cell voltage. So that's the game we're playing here. And so just maybe to show you an outcome of this model, the initial assessment here, essentially what we looked at is to say, well, are flow batteries really the best option here? So I'm looking again at enclosed batteries, which would be my lead acid and lithium ion. This is for 4 hours of energy storage, 5 hours, excuse me. I looked at hybrid, so that's there the zinc bromine, lithium polysulfide, and other non-aqueous hybrid that we haven't thought of yet, but it's a conceptual system. And we looked at full flow, which is this vanadium redox, aqueous redox, and non-aqueous redox. And I think what I want you to take away from this is that clearly what it shows you at 4 hours is that it seems that the open batteries, so the ones that have flow, are going to be significantly cheaper than the batteries that are closed, right? So this is around the time when flow starts to become quite helpful to you. But you can still see that effects of energy density for things like zinc bromine and lithium polysulfide are still playing a role. But what you should take away from this is that we are actually getting, to systems that look like they could begin to approach the target that we've set. The problem is we don't know where to go from here. I've basically shown you a bunch of stacks here where I have an add up of energy cost, power cost, balance of plant, and additions to price. But what's hidden here in this is the analysis as to where cost savings could be. So where do we go from here? And how can I think about how different materials designs, different performance, and different improvements can impact what's going on. So for that, we turn to a little bit more of a detailed model. And this is an explicit design map that we can develop using the same model that I showed you to basically break down where cost savings can exist. So what I'm going to show you here is cell voltage on the y-axis and area-specific resistance on the x-axis. Remember, area-specific resistance is directly proportional to reactor cost, and cell voltage appears in reactor cost in terms of power as well as in terms of the electrolyte. And what I'll show you here is contours of iso concentration in the form of molality, right? So this is moles per kilogram. What I'm showing you here is a viable region for non-aqueous redox flow batteries where you can see that if I have a particularly resistive reactor, it's very difficult for me to get into my design space, but as my reactor becomes increasingly less resistive, at some point in time, I don't need to get any better, and now all of a sudden most of my costs are associated with the cost of my electrolyte. And you can see, for example, cell voltage. As I get to higher cell voltages, my required active species become lower and lower. This is again because I have increasingly energy content in there, and I don't need such a high active species concentration to offset my inactive components. And you can look at these types of analyses then again for something like an aqueous system, where you can see different sensitivities appear. Where aqueous systems, I have a lower sensitivity to area-specific resistance because these are so conductive, they work well enough already. And you can also see that I have a lower sensitivity to concentration. And this is because, again, sulfuric acid and water are so cheap, right? And so the way you might think about that is if I take a cheap component out, even though it's not storing energy, and I put a more expensive component in that is also storing energy, am I actually moving forward? And the answer is it's not particularly clear. What you can do here when you get these types of analyses is break these down into key metrics. So again, for a 5-hour discharge storage, you can say, for example, I need my active species cost to be relatively low. I need my molecular weights to be relatively low, so I don't have that many kilograms that I need to buy of my material. For aqueous systems, we like to have high cell voltage, and we like to have low ASR, area-specific resistance. And for non-aqueous systems, we want to have higher actives concentrations over here. We want to have then, of course, high cell voltages, low ASRs, and we want to have relatively low salt cost factors. Again, because I told you that if I have a fluorinated salt, that's going to be quite expensive. But this now gives me some things to aim at, right? And it gives me some way to go and talk to colleagues who have subdomain expertise to say, hey, you know, what organic materials can you make that are going to be this high concentration in a non-aqueous electrolyte? Or, hey guys, I want to have an organic material that has this relatively low molecular weight and maybe can store 2 electrons per unit molecule. And this is something to design towards. So now it's important to recognize who we are. I'm an academic, and so when I see this big design space, I get very excited. Lots of opportunities. However, if I'm starting a business and I look at all of these uncertainties, I get a little scared. And so what we'll probably see is that there are going to be aqueous, say organic or inexpensive materials will come first, but eventually we'll begin to see non-aqueous systems because there's a bigger design space. So there's a reason to think about why to go one way or the other. I think there's a lot to explore here, but it's still at a relatively early level. So in the remaining time, I want to give you some examples of pathways forward. So I mentioned that we're going to need inexpensive materials, and we're going to need to think a little bit more broadly. This is an example of sulfur, sulfur pyramid that came from the tar sands in Alberta, Canada. Anytime you pull out oil out of the ground, sulfur comes along with it. And depending upon how much sulfur you have, it's either sour, which is a lot of sulfur, or it's sweet, which is not a lot of sulfur. The tar sands are particularly sour, and as a result, we build pyramids made out of sulfur, right? Some of the sulfur goes into things like sulfuric acid and other types of streams, but largely speaking, you know, we don't have that much to do with it. But you can imagine now what you could do in terms of sulfur as an energy storage material. This is what's driving a lot of work in lithium sulfur batteries, but you can also imagine using sulfur for energy storage in terms of redox flow, alkaline polysulfide. You can also think about defining inexpensive redox chemistries using targeted organic molecules, right? So can we use tweaks of organic chemistry to tailor organic molecules that can be relatively cheap and give me high performance? As a chemical engineer, it means that I'm an okay chemist. So a lot of this stuff, I can do some of it, but in this case, I have a lot of strong chemistry partners from a range of different institutions, and of course a chemical engineer as well, who help us begin to move through this design space and understand what we can do with tweaks of organic chemistry. But maybe to convince you that a lot of these materials can be cheap, I'll give you an example. So this is an example of anthraquinone disulfonic acid, right? AQDS. And this, basically the way you form this is you have crude tar coming out of the ground, again, coming from petrochemicals. You can separate out anthracene. You can take that anthracene and oxidize it to form anthraquinone. We actually do this right now. This is a catalyst that we then use to make hydrogen peroxide, right? And so with one more step of sulfonation, you can take this perhaps to a redox active material. And so you can imagine saying, taking anthracene, designing a simple plant process around, so this is something coming out of Aspen, and I can figure out how my costs will come down as a function of my production volume, where at low production volumes, the capital cost is dominating, but as you get to higher and higher production volumes, now we get towards the operating cost, right? And you can see that for my target of, say, $5 per kilogram, I can bring the cost all the way down of these organic materials. And you can then quantify that production cost then to an energy. So, for example, how much energy you can store. And so again, I'm being a homer, University of Illinois. This is 1 day of energy used at Illinois, and you can sort of see this is the kind of batteries that we would need to get there, right? So this gives you an idea of scale. Also, for those of you who are working in this space, I'm going to hurry through the last few slides here, but the point that I want to make is that how we approach these problems is very important. We spend a lot of time thinking about research cells as compared to larger cells like subscale cells and full stacks, trying to understand how do we test materials very carefully. So for example, if Professor Archer gives me some polymer, I can't take that polymer and test it into a subscale cell. It's going to require way too much polymer, and then I'm going to come back and tell him that I want to do repeats, and we're not going to be friends anymore because I've got too much polymer. So I want to think a little bit about research cells, right? Small scale cells where I can do rapid characterization. We spent quite a lot of time thinking about these as flexible platforms with which to understand how to design materials and to rapidly characterize, and fail fast, hopefully quickly, and get to the right types of materials. We've also thought a lot about leveraging flow cells as analytical platforms. This is an example of a full cell test where, for example, if I wanted to do a new active material A here, this new active material, in order for me to test it in a full flow battery, I'm going to need to have a separator and I'm going to need to have a counter electrode material. And so what I do is charge and discharge this material in a dynamic sense and wait for it to fail. But if the battery fails, whose fault is it? Is it your new material? Is it the membrane? Is it the other material? It's very difficult to deconvolute these types of challenges. And so then how do you go towards a better analytical platform? Say, for example, a series of do-nothing machines, where here I have now my material A at 50% state of charge. And all I do is I run it through one side of the cell, oxidize it, loop it back on the other side, and reduce it. And what that allows me to do is steady state cell polarization with a single material so I can understand where resistive losses are coming from in my system and back out what kind of design specs I would need for a reactor. If I wanted to see how long A would live, I can then cycle it in another do-nothing machine. This is a symmetric cell, and what I'm doing here with the symmetric cell is I'm charging and discharging and throwing an ion back and forth across the separator, so I'm essentially flipping back and forth around 0 volts. This allows me to charge and discharge and see how these materials decay, and that way I can figure out the decay of one particular material rather than having everything convoluted together. And of course, to do these, you can think about model redox compounds such as nitroxides, ferrocines that have been modified, or even things like iron chloride. There are lots of different things you can get off the shelf or synthesize quite easily. And so just to give you 2 examples of how you might use this, this is thinking about advancing redox molecules, so going from a molecule that was developed by Susan Odom's group at the University of Kentucky. And typically, through electrochemistry, you would want to understand the reversibility using cyclic voltammetry, and you might want to do bulk electrolysis to understand how much it would store charge. These are all dilute solution type applications. You want to use it in a battery under concentrated conditions, but you want to also have the resources and the detail to be able to really analyze the data. And so what we can do, for example, is take our symmetric cell, and we can look at cycling it against itself at relatively high write capabilities, at relatively high concentrations, and accessing a good amount of my active material, and actually cycling it for quite a long time. This is about 80 hours. At the time, that was a little while. That was quite a while. And so this gives us a pathway for validating new materials. We can also think about using my redox platforms to investigate some things of engineering interest. We can use it to develop simple models to understand resistive losses within electrodes for redox flow batteries, and try to understand mass transport and kinetics in the convolution within porous media. We can use it to do scaling analysis, so being able to figure out how small cells and large cells interact with one another. We can use it to understand electrolyte properties and derive correlations using classical Peckley number, Sherwood number, Schmidt number to understand mass transport and generalized correlations. And we can use it to characterize different electrodes to understand the role of things like microstructure and organization. So it's hopefully a very useful platform that many folks can begin to use. I'm going to finish here very quickly with 3 grand challenges for the people who are in the room and also the people who might be watching this later. I think one of the biggest challenges is going to be guided synthesis of new materials with precise properties. So I told you that we have all of organic chemistry at our fingertips. We can think about designing new materials that can get us to the performance that we want. But it's a big difference between knowing that you can do that and actually being able to do it and to do it effectively. And so what tools can we think about using things like quantitative structure property relationships and genomic approaches to begin to understand how do we accelerate invention or discovery of new materials, and how do we know that these are universal, right? So we need to get to new materials faster and more and better, you know, in a more effective way. The second is, can we think about the way we actually put these systems together? So I spent most of my time talking about monomers or small units that would line up with anion exchange membranes. What happens if we go to oligomers, polymers, or colloids? This will allow me to then get to cheaper membranes, but I need to worry a little bit more about transport, right? And I need to worry a little bit more about kinetics. So where is the sweet spot in this macro architectural design? Do I want to stick with monomers, or maybe is there some sweet spot around here? How do we think about that? And then finally, the elephant in the room is 20 years. I told you that I did my model for 20 years. That was what I thought about. And nobody called me on it yet and said, yeah, 20 years, are you sure about that? You want to bet money that it's going to last 20 years or so? And that comes into a warranty. If I sell you a flow battery and I say it lasts 20 years, I'm going to have to give you a warranty. So when it doesn't, I come and replace it, right? And the challenge is that over time, you have decay, right? So this is looking at capacity fade over time as a function of cycle number. What you see is that there are two different modes of failure. It starts off fading quite fast, and then it starts to slow down. So, okay, there are clearly two different things that are going on. How do I quantify and predict these decay mechanisms before I need to run the battery for 20 years? How do you figure that out? That's going to be another big question as well. So I'm right at the top of my time and even a little bit past it. I want to thank you for your attention. And if I've left you with anything today, I hope that you can see that the benefits of early stage techno-economic modeling in terms of informing research direction and allowing us hopefully to get beyond I need a better battery to what should I specifically go after. Redox flow batteries show a lot of promise if we can get less expensive electrolytes and if we can get the balance of design to come down, but there is a pathway. And then process cost models can be illuminating in terms of trying to understand for the new materials, how can we get to a cheaper system? So even if I have an organic molecule, it doesn't necessarily need to be cheap. I need to figure out the way to actually get to the form that I'd like. So thank you so much. I really appreciate it. It was a pleasure meeting all of you. I'm looking forward to discussions at lunch. And before I leave, I want to thank the group, folks who are presently in the group, folks who have left the group, and of course funding sources as well who have been kind enough to support this research, and a raft of excellent collaborators. Thank you for your time.
So we can take one quick question, and after that all questions would be at lunchtime. So any quick burning questions? All right, good. Well,
Why did the drill turn on?
well, so maybe I'll ask a quick question, right? So the question I had is about, in fact, the very last thing you said, which is the 7,000 hours.
Yes.
Yeah, and so in that case, presumably the cost is not going to be the initial cost, that you will have some way of tuning up?
Right.
Is that the,
And so the vision would be that the capital cost essentially assumes that you don't have, it's an upfront cost, but you also have to worry about operating costs and you have to worry about maintenance, right? And what the thought would be for these types of systems is the capital cost tells you how much you need to pay upfront for the battery, but the value that you derive for that battery is a little bit more complicated of a characterization. But you can imagine that over, let's say, every year or even shorter than that, periodically you could tune up the battery, bring a tech out to clean up the electrolyte, you know, maybe flush the reactors, things like that. And so understanding these decay mechanisms will be important, but arresting them for 20 years may not necessarily be needed. Right. And that's, again, the context.
Good, that's what I thought.
Yeah. Yes?
For grid scale implementation, how big would these tanks actually be?
That's a really good question. So it sort of depends upon the scale of the unit, right, which is sort of a circular answer. So just to give you some sense, a lot of where if you were going to buy a flow battery now, it comes in a containerized solution, which is sort of a shipping container, which has all the whole kit and caboodle. The idea is that you can then take the shipping container and move it to different locations. Within there, you usually have a set of tanks. You usually don't want to have one gigantic tank. You're willing to buy lots of smaller tanks because it's easier to be modular, to add a tank, to take away a tank such as that. the unit size will somewhat be determined by how expensive is the form factor and how much you're worried about well mixing assumptions and things like that.
All right, good. Thank you. Very good.
Thanks. Thank you.